So we're analyzing the wrong enantiomer or the undesired enantiomer. So the isomer ratio is typically like 100 to 1 or 1,000 to 1, 2,000 to 1. So analysis of racemate is by comparison easy to analyzing for the minor enantiomer. And in this example, this was on a separation, I think on a chiral pack IA, as we decrease the amount of IPA or isopropyl alcohol, we make the mobile phase weaker and we get kind of an expected increase in retention. And we also have an increase in separation. So we have several conditions that we can choose. This is fairly straightforward. Notice that we get a little more tailing. Notice the peaks are a little shorter. Part of this, I think, is a little bit of column overload. I had shot a very concentrated sample just because I didn't know how much response I was going to get. So the analysis of the low-level enantiomer is a bit of a challenge. And for these two enantiomers, excuse me, for this pair, we got nearly baseline separation. If you just look at the chromatogram, you say, well, this is penetration to baseline. We do that all the time. Peak height was about 1,500 milliabsorbance or 1,500 milliabsorbance units. So this is only a fraction of the peak height. So this is an insignificant amount of area of this peak that bleeds into this peak, but correspondingly, you get a similar amount of area from this peak bleeding into this one. So penetration to baseline is a reasonable way to do the integration for these two peaks, and it's very reliable. The peaks get smaller, and there's not quite as much tailing. Peak width's a little sharper just because of the column overload problem. So it's not a problem, but at low-level components. But think about what happens as we bleed some of this isomer into this more retained peak. So notice that we get a little bit of, so you just kind of extrapolate the exponential decay in from this peak into here, and you think, well, in this region here, we get a little bit of this contribution of this peak to the area of this peak. At say 2%, it's probably not significant. It may be measurable, but it's not very, very large. But what about at 0.1% or 0.2% or 0.1% or 0.05? You can see that could be an appreciable area, and we would have bias the retention, bias the area high. But if we look at how much the front peak or the tailing peak bleeds into the front peak, we see, well, that's not so much. And in fact, you can see that these peaks probably have no bleed of the later eluting peak fronting into the second peak. So in general, we would want to have our low-level enantiomer elute first if we can. Two advantages: one, the first peak is usually taller, and the other is there's less interference from the later eluting peak. Can't always do that, but at least you need to be aware that you can have some tailing of the first peak into the second peak. And good LOD, LOQ requires quiet baseline. We'll talk about this a little bit more in a later slide. So now we'll talk a little bit, these are some of the issues around chiral chromatography. So now we want to talk a little bit about validation of analytical methods. So much of what we've done in chiral chromatography, we're going to do here. We'll worry about things like precision, things that are related to the accuracy, limit of detection, the robustness of the method, the stability of the sample. So I'm not going to go into the precision because that's fairly straightforward. I think most people are well aware of these things, but we do want to know how good our when we run an analysis and we make multiple injections or multiple preps, is this reliable? What about if is this going to be a technique dependent? Is it really going to matter how the analyst actually performs the experiment? There's some really technique dependent steps. What about the equipment? Does it matter whether you use a UHPLC or a more instrument that maybe came from a previous century and has a little extra column band broadening? Does it matter, or maybe a longer delay time? Is there a lot-to-lot variability, and so on? And then certainly the collaborative study between laboratories. So these are things that we worry about in achiral chromatography. We also can worry about them in chiral chromatography. Accuracy, these are related to the accuracy, this is getting reproducible results, this is getting the right result. And so these, there may be a few issues just because we're really dealing with a low-level component, but it's no different than we would treat impurities in achiral chromatography. So we want to demonstrate good resolution between the isomers. And as I talked about before, that, for two major components, that's probably pretty good. It's probably pretty good if we have two level components. We might have a problem if we have one high and one low. But enantiomers have the same UV spectrum. They're just mirror images, so the UV spectrum in a chiral solvent will be identical. They have the same mass, so you have the same mass spectrum if you analyze them by mass spectroscopy. They will have opposite rotation. If they're the same level, you'd expect similar rotations. And if you have a racemate, you would expect them to have the same UV area. And so you want to maybe confirm all of those things. I think that's pretty straightforward. It's almost too easy. I don't want to get into this, but there's something about enantiomeric excess, and sometimes people report the results in chiral separations in enantiomeric excess, and it's archaic, but it's not wrong. It's an acceptable way to do it. I think it's unnecessary, and I think it actually is. It's just confusing, but the transformation between enantiomeric excess and chiral purity is doable. We use the same numbers. It's just we look at the difference between the desired enantiomer or right enantiomer and the wrong enantiomer divided by the sum of the two enantiomers times 100%. And this comes from pre-chiral chromatography days, when the only way to measure the enantiomeric excess or the enantiomeric purity was to do an optical rotation based upon what you would expect the optical rotation to be. The wrong enantiomer gives opposite response for the desired enantiomer, and it kind of cancels out. So how much rotation you get is just the difference between the two enantiomers. For racemate, there's no optical rotation. But it is archaic, and it is a little confusing. I think a more reasonable way to do it is just measure it as a chiral purity, like you would any other impurity. Just the area or the response of the wrong enantiomer divided by the concentration of the area of the correct enantiomer. Probably should use correct instead of right, because the right-handed, left-handed issue, but of the correct enantiomer times 100%. And I think just treat it like a regular impurity is the way to do it. But people do it both ways, and we can get into a discussion about that. It's not worth it. I think either way is, the numbers are, you can transform them. It's like the difference between Fahrenheit and centigrade. So linear range, we are dealing with the ratio, so we are really dealing with the area percent, but the dynamic range of UV detectors on the order of 1,000 to 1,500 milliabsorbance units. That makes 0.1% on the order of 1 milliabsorbent units. So the dynamic range will depend on the signal to noise of the minor component. And so an LOD and LOQ obviously depend on the signal to noise. So the couple of issues around signal to noise, and it does require a quiet baseline, for example, or you can increase the signal to noise by having a quiet baseline. And one of the things that we want to do is, and this is an achiral compound, I just chose this spectrum because it has some things I want to point out. But you want to change the UV, you want to obtain the UV spectrum if possible. So you want to select a wavelength with good response. Well, in this region around 200, usually the diode array detectors, for example, can sort of go down, well, they can go down to 190, 200 region, but most of the solvents we have absorbance in this region. So their UV cutoffs are somewhere around depending on what solvent it is. Methanol, I think, is around 205. So you may get some response background due to the solvent. Just attenuate your response. It shouldn't interfere. They won't, but we usually want to use a wavelength a little longer than, say, 200 nanometers or 210 or something like that. We want to use a wavelength around, it's a little longer than that. It's above the UV cutoff of the mobile phase, and it's also not in a region where everything absorbs. So you're not going to have as many bumps in the baseline. If you have things in the mobile phase, such as diethylamine, trifluoroacetic acid, they can cause some disturbance of the baseline, some background response. And I think if you observe, probably has observed that with TFA in the mobile phase below a wavelength of, below 220 or something like that, the baseline is a little noisier than it is at longer wavelengths. People sometimes choose 254 nanometers as their wavelength, and this comes from in the old days, we had just single wavelength detectors, and they used a mercury lamp and a really sharp emission band at 254 point something nanometers. It was very quiet. It was an excellent detector if your analyte had good absorbance at 254. With the deuterium lamp, we don't get, 254 is not a special wavelength for the deuterium lamps. There's no real reason to choose 254. It's just a historical wavelength, and people often choose it. In fact, for this compound, it would be a poor choice if we're trying to improve sensitivity because it has very poor absorbance. We probably want a wavelength around here. Notice in aromatic compounds, we often see somewhere in here we have some absorbance by aromatic compounds. So if you have a lot of impurities that are aliphatic, and you just want to focus on the aromatic compounds, you might want to use this. But I think get a UV spectrum, so you deliberately choose a wavelength. If you don't have a UV spectrometer, you can use a very short column. It doesn't even have to be a chiral column. You can use a reverse phase column, for example, and obtain wavelength or a guard column even, and just inject your analyte repeated injections at different wavelengths, and you can kind of manually construct at least an approximation of UV spectrum.